Cloud of smoke with its own mind is just shooting through the sky. This is absolutely incredible. Again, you're watching the SpaceX Falcon 9 rocket launch from Vandenberg Air Force Base, this visible from Bakersfield.
It looked like a star in the heavens.
Seth Putterman called it the star in a jar, a tiny spot of bright light contained in a flask of liquid. This star in a jar is made when a sound wave is passed through a small bubble inside a flask of liquid. And this sound wave makes the bubble do something remarkable. First it expands, then it collapses. And this collapse happens so violently that vapor molecules trapped inside the bubble slam together and heat up so much that the bubble gives off an incredible burst of heat and light, several thousand times a second, giving the appearance of a star.
Also, the phases of water. Now, we've all learned that there's a solid phase, a liquid phase, and a vapor phase. However, 100 years ago, there was some idea that there might be a fourth phase somewhere in between a solid and a liquid. Sir William Hardy, a famous physical chemist, 100 years ago exactly, professed that there was actually a fourth phase of water, and this water was kind of more ordered than other kinds of water, and in fact had a gel-like consistency. So the question arose to us, you know, all of this was forgotten because people began, as methods improved, to begin to study molecules instead of ensembles of molecules. And people forgot about the collectivity of water molecules and began looking, the same as in biology, began looking at individual molecules and lost sight of the collection. So we thought, we're going to look at this because we had some idea that it's possible that this missing link, this fourth phase, might actually be the missing link so that we can understand the phenomena regarding water that we don't understand. So we started by looking somewhere between a solid and a liquid. And the first experiments that we did that get us going is we took a gel, that's the solid, and we put it next to water. And we added some particles to the water because we had the sense that the particles would show us something. And sure enough, you can see that what happened is that the particles began moving away from the interface between the gel and the water, and they just kept moving and moving and moving, and they wound up stopping at a distance that's, well, roughly the size of one of your hairs. Now that may seem small, but by molecular dimensions, that's practically infinite. It's a huge dimension. So we began studying the properties of this zone, and we called it, for obvious reasons, the exclusion zone, because practically everything you'd put there would get excluded, would get expelled from the zone as it built up, or instead of exclusion zone, EZ for short. And so we found that the kinds of materials that would create or nucleate this kind of zone, not just gels, but we found that practically every water-loving or so-called hydrophilic surface could do exactly that, creating the EZ water. And as the EZ water builds, it would expel all the solutes or particles, whatever, into the bulk water. And we began learning about the properties, and we've spent now quite a few years looking at the properties. And so it looked something like this. You have a material next to water, and these sheets of EZ layers begin to build, and they build and build, and they just keep building up one by one. And so if you look at the structure of each one of these planes, you can see that it's a honeycomb, hexagonal kind of structure, a bit like ice, but not ice. And if you look at it carefully, you can see the molecular structure. So of course it consists of hydrogen and oxygen because it's built from water. But actually, they're not water molecules. If you start counting the number of hydrogens and the number of oxygens, it turns out that it's not H2O. It's actually H3O2. So it is possible that there's water that's not H2O, some phase of water. So we began looking, of course, more into these extremely interesting properties. And what we found is we stuck electrodes into the EZ water because we thought there might be some electrical potential. And it turned out that there's lots of negative charge in that zone. And we used some dyes to seek positive charge, and we found that in the bulk water zone, there was an equal amount of positivity. So what's going on, it looked like, is that next to these interfaces, the water molecule was somehow splitting up into a negative part and the positive part. And the negative part sat right next to the water-loving material, and the positive charges went out beyond that. We found, actually, it's the same. You didn't need a straight interface. You could also have a sphere. So you put a sphere in the water, and any sphere that's suspended in the water develops one of these exclusion zones, EZs around it, with the negative charge. And beyond that is all the positive charge separation. It didn't have to be only a material sphere. In fact, you could put a droplet in there, water droplet, or in fact, even a bubble. You get the same result. Surrounding each one of these entities is the negative charge and the separated positive charge. the water bridge, if you think of it as plain old liquid bulk water, it's hard to understand. But if you think of it as easy water and the gel-like character, then you can understand how it could be sustained with almost no droop. It's a very stiff structure. And one day, we're doing an experiment, and a student in the lab walks by, and he has this lamp, and he takes the lamp and he shines it on the specimen, and where the light was shining, we found that the exclusion zone grew. It grew by leaps and bounds. So we thought, aha, it looks like light. And we did many experiments to show that the energy for building this comes from light. So in other words, you have the material, you have the easy water, and you collect energy from outside. And as you collect the energy from outside, the exclusion zone builds. And if you take away that extra energy, it'll go back to its normal size, charged by light, by the sun. It's a gift from the sun.